what you do to find the answer to a random question. Like if I ask you, will I flip a head or tail? This is the question, and the experiment is actually the act of flipping. Okay, flipping the head and looking at the result. Okay, and the outcomes basically are the results, and a number of different outcomes together collectively make up the events. Okay, and we went into some, we presented some examples, and this was the example that we did with 2 cards, that everyone in the class took 2 cards, and we played a game using that, and one of the students actually ended up winning. And so those were the rules of that game. Okay, so I'm not going to go through those, but basically these are the stuff that I want you to know from counting. Okay, if you have equally likely events, okay, the probability that event A occurs is basically the number of different ways that A can occur divided by the total number of outcomes. Okay, and this comes up over and over again in probability. Okay, this comes up over and over again in probability, and this is in essence what the probability is all about. So, for example, if you draw 1 card from a deck of cards, what is the probability that you draw an ace? Okay, so the way you calculate this probability is that the number of aces in the deck divided by the number of cards in the deck. Okay, so this part of probability, which is combinatorics, is more or less you understand it unconsciously because humans are good at counting, and you can do it no problem. And the way what we did here was that we tried to come up with a systematic way of counting. So we divided these counting methods into 2 parts. One part was where order matters, we call those permutation, and one part is where order doesn't matter. Okay, and that's combinations. Okay, so we try to make this counting more formal, basically. Okay, and then when we have when order matters, we have also 2 cases, with replacement or without replacement, and also for when order doesn't matter, we just consider the case when without replacement. Okay, there is a case with replacement, but we didn't cover it. Okay. So these problems, more or less, I think you guys are good at. I mean, based on your assignment, I think assignment 7 was involving these problems, and quiz 7, you guys did good in assignment 7 and quiz 7. And I think the reason behind it is that you might not know this systematic way of doing things, but unconsciously you know what to do, and you do it. And as long as you do that without systematically following this, I'm okay with it. Okay, but it's up to you to test yourself and to see whether you do understand it or you can solve problems, basically. Okay, so we saw some examples of permutation, like coin flips. We said if you have 2 coin flips and we want to count the number of heads, and so what is the probability of getting 2 heads? So these are the cases we can, in the first toss we can get a head or tail, and then for the second toss again we can get a head or a tail. And when you combine all of these, you see you have 4 possible outcomes, and out of those 4 possible outcomes, there's only one case where you have 2 heads. So it's 1 divided by 4. Okay, so these things you do basically, and if you want to do it systematically using the counting methods that I told you, it would be 2 to the power of 2 and 1 over 2 to the power of 2, because you have 2 flips, and each flip can take 2 possible outcomes, either a head or a tail. That's why it's 2 to the power of 2. So that's the systematic way of doing it. But again, it's up to you. So for 3 cases, it's 2 to the power of 3, because you have 3 spots, and each of those 3 spots could take 2 possible values, and therefore you have 8 different outcomes. So that's why you see here 8 different outcomes. Okay, and you can also use these tree diagrams. I mean, if you're comfortable using these tree diagrams, by all means, go ahead use them. You know, you could divide events. The first event is the first toss. The second event is the second toss, and so on. Like the first experiment is the first toss, second experiment is the second toss, and so on. Okay, so it's up to you. If you feel comfortable dealing with these tree diagrams, do it. But like I said, the systematic way of doing it is like you have three spots, and each of those spots could be either a head or a tail. Therefore, in total, you have 8 different possibilities. Okay, and one of them is all heads, basically. So we saw a number of different examples using permutations, and basically this is the case where order matters and we replace. So by replacement, for example, for tossing a coin, I mean if you flip a head in the first toss, you can flip a head again in the second toss. So the possibility of getting a head is again considered for the second toss. Okay. So in those cases, the number of possibilities is basically number of possible outcomes per event. So in the case of flipping, it's head or tail. So there are 2 to the power of the number of events. So the number of times you flip. So if you flip 3 times, it's to the power of 3. If you flip 4 times, it's 2 to the power of 4, and so on. Okay. So that would be without replace. Now we're going to consider the case without replacement. So we consider the case with replacement, now without replacement. Okay. So without replacement is like when you take someone out of your selection. So here we said we're trying to seat the panelists, some 5 panelists in a row. Okay. So we have 5 panelists, and there's this debate, and we want to. We want to see how many different seating arrangements are possible. Okay, so here is an example of permutations without replacement. The reason is once I have 5 different seating spots available. Okay, I have 5 different seating spots available, and once I fix a seating spot, so I have 5 available. Okay, and I have these panelists A, B, C, D, E. Okay. Once I sit the first person at the person A at the first seat, A is out. Okay. So that's the case without replacement. Now I have to in my second seat I have 4 possible choices, not 5. Okay. So in head or tail, if this was a head, here I could also flip a head. That's without replacement. And so that's with replacement, sorry. And this is without replacement. Okay? So we basically, these are like making the counting method systematically. But like I said, like most of you do it unconsciously. Okay? So the example showed you that they're like you can sit down and count them one by one, but the problem becomes complicated quickly. Okay? So for 5, it's not that easy to count all 5. There are many different cases. Okay, so another way we tried to do it was using trees, and again, using trees quickly the tree grows and becomes big. But generally, this is how you could do that. For the first possible seat, you have 5 choices. Once you fix that, for the next seat you have 4 choices. For the next seat you have 3 choices, and so on. That's why it becomes 5 times 4 times 3 times 2 times 1, which becomes 5 factorial. Okay, so you can see that we're trying to systematically count, and that's basically what we come up with. So when we're dealing with without replacement case, we're basically multiplying. Sometimes you might not have 5 seats, okay? So say you have 3 seats instead of 5 seats. So still you have 5 panelists, but instead of having 5 seats, you have 3 seats. And I ask you how many different ways you can seat these 5 panelists into these 3 seats, okay? So again, this would be the answer, because for the first seat, you have 4 choices, 5 choices. For the second seat, you have 4 choices. For the third seat, you have 3 choices, okay? So the way you do it is you take your 5 factorial and you divide it by 2 factorial, which is the number of different seats that we remove. Okay? Or you can think of it like this. 5 factorial divided by 5 minus 3, the number of seats factorial. Okay? So the number of people who we are sitting the number of basically panelists minus the number of seats factorial. So that would be the systematic way of doing it. Like I said, most of you probably do these questions without following these systematic counting methods, but still, it's up to you. If you want to follow these methods, it's up to you. And you can see when you have 5 people and 5 chairs, it becomes 5 factorial over 0 factorial, which is the 5 factorial. Okay? So, again, the examples I'm not going to go over. So these examples you could go over yourself, but all we're trying to do is we're trying to come up with systematic ways of counting. So, yeah.
Would you say any of those examples are ones we'll most likely see on the exam?
Yes.
Something relative to it?
I mean, all examples are important.
But what would you say is like the most important?
The most important. Everything is important in the course. No, still, I mean, you might not see a question on counting directly, but the thing is, once you go to probability, you're still using counting to calculate the probabilities, right? So you might see a question on probability, for example, even on random variables, where you have to use counting to get the number of different permutations or combinations. Yeah.
When you say random variables, probability is more important than just regular one?
Basically, I mean, the thing is, once we started probability, we built on top of what we learned. Okay? So the first thing we do is we learn how to count. Okay? And like I said, most of you know this naturally. Then once we know how to count, we learn how to calculate probabilities based on counting. And once we know how to calculate the probabilities, we introduce random variables. So you can see it's like a deck of cards that we're building on top of each other. So I could give you a question on random variables that could easily have this combination inside of it, that could have probability inside of it, and so on. So that's why, like I'm telling you, like all of these examples are important. So the reason I don't want to be very specific is because, like I said, if as soon as I become specific about problems, first of all, I can't be very specific. Second of all, there's going to be someone who will come after the final and complain, you told us that this was very important and there wasn't a question about this. So
to be very specific,
yeah. But I mean, what I've done so far throughout today's review, I've highlighted the important stuff. So if you were listening to me closely by now, you know at least half of the questions in the final. Okay. So again, when we go to the case where order doesn't matter and without replacement, things become like this. Okay, when we are choosing, for example, R things from N things. Okay, or we say N choose R. From N things, we choose R, basically. And by the way, guys, make sure all of you know how to do N choose R in your calculators, okay? Because you have to do these N choose R's using calculators, okay? So make sure, and most the calculators have this. Like, make sure just you know how to use your calculator and how to do the N choose R. And if you don't, bring your calculator with you on Wednesday, tomorrow, during the lecture, and I'll show you, if your calculator has it. So for combinations, again, things are like this. How many different ways can you choose 2 cards from a deck of cards when order doesn't matter? Okay, when order doesn't matter. So these are the type of questions you will see, and it's basically 52 cards we have, and we're choosing 2. So the answer is 52 choose 2. Okay, the answer is 52 choose 2. And I basically showed you why it's 52 choose 2. Okay, I'll show you why there's 52 choose 2. So these slides, again, you can go over, and this is the formula for choose. So N choose R is basically N factorial divided by N minus R factorial. And yeah, go over these examples yourself. Like I said, these examples, by themselves. You might not see a problem on these examples by themselves, but later on, I mean, when we learn about probability, you still use these in probability. Okay? For example, when we are dealing with binomial distribution, we are using the choose operation. Okay? So, that's that. So after combinatorics, we started talking about probability. Okay? And we introduced the axioms of probability. Okay, so again, we talked about what is a random variable or random, what is randomness basically. And then we introduced this. Okay, so we said that if we have an experiment, the sample space is all the possible outcomes. So all the answers that your experiment could have is your whole sample space. And inside your sample space, like I said, are these little dots which are the possible outcomes. Okay? So for example, I'll show you an example later. And we said bunch of these, collectively, bunch of these outcomes can make up an event. Okay? Can make up an event. So let's consider a die. Okay? So in the example of rolling a die, okay, the sample space is basically this. I could either roll a 1, a 2, a 3, a 4, a 5, a 6. Okay, so that's the whole sample space. There's no outcome outside of this which could happen when I roll the dice. Okay, I could not get a 7, or I could not get a 0, or a -1. Okay, and the event is a collection of these individual outcomes. So for example, the event that the number you roll is odd is basically when the outcomes are 1, 3, or 5. Okay, and the event where you roll a 1 is basically just the event 1, and the event where you roll a number between 1 and 6 is basically the numbers 1 through 6, or the whole sample space, right? And then we said we could use Venn diagrams to represent the sample space. So the whole sample space is basically the square, which is the whole Venn diagram, and the probability of the sample space itself is always 1. So I mean, when you roll a dice, you either going to get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So the probability of getting a number between 1 and 6 is 1. You always get a number between 1 and 6. Okay? So that was the example that basically says probability of getting it is 6. And using the Venn diagram, you can see we have the numbers and so on. And we also said we could have an empty set. Okay? And the probability of getting an empty set is 0. So that means when you carry out an experiment, an outcome will happen. I mean, something's going to happen. So when you roll a dice, you're going to roll something. It's not the case that you're not going to get anything as the result. So the probability of the empty set is 0. Okay? So the other things that we said was that if we have an event A, okay, which we show using this, so basically some sort of a circle in the Venn diagram, and the probability that your event A is between 0 and 1, because the probability of the whole sample space is 1, the probability of the empty set is 0, and the probability of the whole thing is, the probability of A, the event A, is between 1 and 0. For example, probability of rolling an odd number is 0.5, because you could roll a 1, a 2, a 1, a 3, a 5. Okay? And that's represented in Venn diagram using again this. So guys, anytime you feel you're very comfortable with the topic, let me know and I'll skip it, okay?
Sir?
Yeah.
Are we going to have to draw a Venn diagram like that? Show the sample space and outcome?
No, I'm not going to ask you to draw Venn diagrams. I'm going to ask more advanced questions. You're better than that, actually. In probability, at least you guys are very good at it. So this is another example. So we have when you have a complement of event. Okay, this is very important. When you have a complement of an event, you basically do the probability of the complement is 1 minus the event. Okay, the probability of the complement of an event is 1 minus the event. And then if you have an intersection of two events, that's basically this area represented here. It's a probability that both events occur. Okay, both events occur. Okay. Then, so this is an example of two events occurring. So what is the probability of rolling an odd number and a number that's greater than 4? So it has to be odd and it has to be greater than 4. So this is the probability that a number is greater than 4. So it contains 5 and 6. I mean, this is the event that it's greater than 4, and this is the event that is odd. And you can see where they intersect. That's basically the outcome. Okay. So we also talked about the union of two events. Okay, which is basically the whole event. So probability of rolling an odd number or greater than 4, it's basically the union, that's the whole thing. And last thing is probability of A minus B. It's basically the events that are in B but not in B. The probability of A minus B is probability of are the events that are in A but not B. So that's that area. And we have an example for that as well. So let me go quickly over these. I guess the rest of these are okay. So these stuff I think you're good at. Okay, so this is basically the 3 axioms of probability. And the 3 axioms state that the first one says the probability of any event is between 0 and 1. Probability of the whole sample space is 1. And if you have a bunch of mutually exclusive events, that means events like this, events that do not overlap. Okay, so if this is your sample space, if your events A and B do not overlap, those are mutually exclusive, that they don't have any elements in common. Okay, so if you have a bunch of those, the probability of the union is basically the sum of individual probabilities. So we also said, this is again the way we calculate most of our probability. We said when we have equally likely events, the probability of the event is the number of outcomes in E divided by number of outcomes in S. Okay, so you count, and that's here you see where those combinatoric stuff, those counting methods come in, because you have to count the number of outcomes in E, and you have to count the number of outcomes in S, and that's where you'll see this. Okay, and then we saw some examples again. These examples you could go over yourself, because I like to get to the more advanced stuff. So, how far I went into this lecture? Okay, I see. So now we get to the more important stuff. So, how to conditional probability. So guys, this conditional probability is important, okay? So conditional probability, basically we say probability that the event E occurs given event F occurs, okay? So basically in conditional probability what happens is that we make some observation about some other event, F, okay, and we see that this event occurs. And then we want to see, now given that this event F has occurred, what is the probability that the event E occurs? Okay? And the way you calculate this is using this formula. So you calculate the probability that E occurs and F occurs divided by probability that F occurs. Or probability of E intersection F divided by probability F. Okay? And there's an example for that. So these examples, please go over yourself, but conditionally probability, guys, is important. Now, this also is very important, the law of total probability. Okay? The law of total probability basically says that probability that the event E occurs is equal to the probability that E occurs given F times probability of F plus probability of E occurs given F complement times F complement. Okay? So again, this is an important this is a important concept. Okay, make sure you're looking at this. Okay, so we saw an example of this as well. So let's go through this example. Due to an internet configuration error, packets sent from New York to Los Angeles are routed through El Paso, Texas, with probability 3/4. Given that a packet is routed through El Paso, suppose it has a conditional probability of 1/3 of being dropped. Okay, so here you can see that given it's routed through El Paso, if we observe that it's routed through El Paso, it has 1/3 chance of being dropped. Okay, and given that the packet is not routed through El Paso, suppose it has a conditional probability of 1/4 of being dropped. So if it's not routed through El Paso, if we observe that it's not routed through El Paso, then it has 1/4 chance of being dropped. Okay, find the probability that the packet is dropped. Okay, so does any of you want to volunteer to do this question? It would be a good practice for the final, by the way. Does anybody know how they could solve this question? You don't have to solve it. No. Bayes, no, we haven't learned Bayes here actually. It's the total law of probability. Okay, so let's do this one. Okay.
I should take a complement of the probability.
Complement of the probability?
Or 1 minus.
Yeah.
Put the formula.
So you have if we
You have
go
to-
to Paso.
So, but in these questions, questions like these, so this one is not dealing with random variables, right? So in questions like this, what you need to do is you need to specify your events. If you have random variables, specify what your random variable is. If you have a question like this, specify what your event is. Yeah.
Could you possibly use the tree method here, since you have two?
You can use tree method as well. You can use tree method as well, but if you use tree method, be careful because you're given conditional probabilities. Okay, you're not given probability of individual events, but you're giving the probability given that you've observed some other event. Okay.
The event it travels through El Paso and it doesn't.
Okay, so that's good. So let's call it E for El Paso. The event that it travels through El Paso or not through El Paso. So if E is the event that it does travel through El Paso, and E complements not through El Paso, right?
Yeah.
So it would be travels El Paso. Okay. Now travels through El Paso. So what is the other event? What are we trying to find? Find the probability that the packet is dropped. So you know that one of the probabilities is going to be the, actually I don't have to solve it in the board. I think I've done this. So E is the event that the packet is routed through El Paso. Okay, so we defined E. What is the other event that we have to define?
It's not rather through
Sure, but that would be basically E complement. Because E is true, yeah.
The packet gets dropped.
The packet gets dropped, right? Because, I mean, you're right, we have to define that, but that could be represented as E complement. That would be the complement of, right? You see why, right? Because the packet either goes through El Paso or doesn't. Because of that, this captures it. This E captures it. Okay? So the other one is that the packet is dropped. Okay? The other one is the packet is dropped. Now, what does the total law of probability tell us? It tells us basically, tells us this. Okay? The probability of D is equal to the probability of D given E times probability of E plus probability of D given E complement times probability of E. Now, let's, I mean, when I read it like that, you guys don't get it at all. because you guys are not good with mathematics. Now let's read it like this. Probability that the packet is dropped is the reason we get this formula is because this is equal to probability of F and this is equal to probability of F intersection E, which is the original formula for the conditional probability. Okay, so again, in the same example that we had, the example from the routing through El Paso and routing not through El Paso, if I ask you, find the conditional probability that a packet is routed through El Paso, given that it has that it's not dropped. Okay. Find the probability that the packet is routed through El Paso, given that it's not dropped. So what does the question ask for? It asks for the probability that it's routed through El Paso, right? Given not dropped. Okay? So this is what the question wants you to calculate. And according to the Bayes rule, which we just showed, that's basically equal to probability that, so I'll write it down here. That's equal to probability that it's not dropped. Okay, you just replace the not dropped and El Paso. Given it's routed through El Paso, okay, times probability of El Paso, okay. So all I'm doing is I'm using this formula. Okay, I'm using this formula. Okay, and instead of using E and F, I'm just using English. Okay, divided by probability that it's not routed, no, sorry, not dropped, given so now given El Paso, probability of El Paso plus, so this is the term basically up here. This basically goes in the denominator. So instead of writing it, because it takes a while, so this whole thing goes to the denominator. This whole total of probability that we calculated before goes in the denominator. Okay? So make sure you're comfortable with these two. Okay? Now, that's 17. Now let's go to 18. So 18, again, we consider the sample space, the events, and so on. And then we talked about the independent events. And then again, independent event is important because basically, two events we say they're independent if the probability of event E and F could be written as the probability of E multiplied by probability of F. And that's the definition of independence. If they don't satisfy this property, then they are dependent. The two events are dependent. Okay? And because another way you could show that that two events are independent is like this: probability of E given F, because this becomes the numerator becomes probability of E times probability of F and the probability of F and probability of F cancel, becomes probability of E. So probability of E given F is equal to probability of E. In other words, if we know that the event F has occurred, okay, that doesn't change the probability that E occurs. That doesn't give you any extra information. That doesn't provide any information about the event. Okay, that doesn't change the probability of E. So an example is rolling a dice, okay, or a die. Basically, the probability, what are we looking at? Rolling a 1, okay? So what is the probability that you roll a 1 in the first time you toss it, and you roll a 1 in the second time you toss it? Okay? The probability of the intersection of these is the individual, because these are independent events. These are you just multiply 1 over 6 with 1 over 6, and then you get 1 over 36. And when you think about it, it makes sense. If you roll a die once and you get a 1, that doesn't change the probability that you get a 1 in the next time you pass. Okay? So there's some more examples, and I guess this lecture was only on probability. After that, there are like a ton of examples on independence. And then we introduced random variables. Okay, so we said basically for random variables we started with discrete random variables, and we said basically we are interested in numerical outcomes of some events, and we map the events to some numerical value. For example, the number of heads in tossing 3 coins. And when you map it to the real line or a real number, when you map your outcomes to a real number, then you have a random variable. Okay? And there are like a bunch of examples of random variables. So guys, do you want me to go over these, or you want me to solve some example problems? I think, like 3 hours is a long time, and I think you've reached your threshold. So if I talk more, I mean, probably it's not going to sink in anyway. So it's better if I do some examples. Yeah, but it's up to you. If you want me to continue, I'll continue. Examples? Okay. So,
sorry.
Yeah.
How many more lectures are there after this?
I think there are 3 or 4 more.
So are you saying you're just going to jump to doing different examples that people have questions for, and you're going to stop going through?
Yeah, I can. It's up to you guys. If you want, I can continue on like this and finish, or if you want, I can solve on some examples. So one example that I'm going to solve, which is assignment, or was it assignment or
quiz 9?
Quiz 9. Okay, quiz 9.
Quiz 9 has probability and random.
Yeah, so quiz 9 has a probability and random variables.
Is it possible to just go through the slides like really quickly and just say like, make sure you know this for the exam kind of thing?
Okay, sure.
Just
Sure. Yeah. So make sure. Let's go over these random variables quickly, and let's see. So let me bring up the PDF versions, because then I can go through it more quickly. So from the PDF version, from random variables, just generally, like I said, know what a random variable is. Okay, be able to describe it. And let's see, so here basically we define random variables. We give a couple of examples of what a random variable is. And we also talk about how we calculate the probability of random variables, which again we use counting to come up with the probabilities of random variables. And we define 2 types of probabilities. Okay, one is when x is equal to x, so when your random variable x is equal to a particular value, and one is when x is less than or equal to x. So when your random variable x is less than or equal to some value. Okay, so know the difference between these two, and know the notation. Generally, uppercase letters are random variables, lowercase letters are a particular value. Okay, and then we talked about discrete random variables. So we said there are 2 types of random variables, continuous and discrete, and then we focused on the discrete one, and the discrete ones are the ones that take on a particular value, like integer values. Okay, and then there are some examples of these. So for example, this is a good example that give you a good overview of discrete random variables. Okay, and this is a very good example that will give you an overview of random variables. And you can see here, like you were asking me, do you need to know those combinatorics, or are you going to see a question on combinatorics? And you can see here, with discrete random variables, I'm using the choose operation to count the number of different ways that x could be equal to 0. Okay, and that's where that's the type of questions you will see. I mean, I'm not going to ask you a question specifically on combinatorics, but a more advanced question which uses that. Okay. Then we define probability mass function. So you should know, guys, what the probability mass function is, because it's important. Okay. So you should be able to describe what the probability mass function is. and it's basically the probability. It's a function, and it's a probability mass function is a function, and it's a function of your random variable, okay? And it gives you the probability of the probability for each random variable. So for each possible value, your random variable, and this is the discrete random variable. The probability mass function is for discrete random variables. For each value your xi could take, it will give you the probability, the corresponding probability. Okay, so know what that is.
So we're going to have to apply that in an example, or just the definition of it?
You should know the definition, and I guess, I mean, this you have to use in, for example, when you calculate expected value, right? When you calculate expected value, you use x multiplied with probability mass function and the summation of it, and you'll see that later, okay? You'll see that later. So probability mass function is important, and these are basically the properties. It's between 1 and 0 for every point, and the sum of all the numbers in the probability mass function should equal to 1. Okay, should equal to 1. And this cumulative distribution function is also important, and it says essentially the probability mass function was the probability that x is equal to x. This one is the probability that x is less than or equal to some x. Okay, this is the difference. Also, for discrete random variables, okay, the probability mass function is discrete. But this cumulative distribution function, it's continuous. Okay, it's continuous. And there are some examples regarding this, and this is, for example, a plot of the, you can see this one is continuous, right? The probability mass function up here is discrete. Okay?
Sir?
Yes?
Do we need to know how to plot the two functions?
I mean, if I give you something like this, okay, you should be able to plot it, right? And you've done examples like this in your assignment. So this was, for example, one example that I think I solved, and there was an example like this in your either assignment or practice question. I think it was in the assignment.
Question 1 in your assignment.
Yeah, I think it was one of the questions in this. So, like I said, guys, the questions you'll see in your final is not going to be something you haven't seen before. It's going to be similar to something you've seen either in my slides as an example, or the practice questions, or the assignment, or the quizzes. Then we talked about the expected value. So you said where probability mass function comes in, you can see it comes in this formula. So when we calculate the expected value of x, we multiply the value of x with the individual probability distribution functions, or actually individual probabilities. You can think of it that way. So expected value and variance, two things you should know. Okay, so not this form of expected value, but expected value and variance. This formula for variance, you should know this. Okay, so know that you know how to calculate expected value and know how to calculate the value. Variance is expected value of x squared minus expected value of x, the whole thing squared. And also know the difference between the expected value of the discrete random variable and the continuous random variable. The expected value when we are dealing with discrete random variables is a summation. For continuous random variables, it's an integration. Okay? Make sure you know the difference. If the random variable I give you is discrete, you should use the summation. If it's continuous, you should use the integration. And also you should use the probability density function. And variance is basically the square root. Standard deviation is the square root of variance. Standard deviation is the square root of variance. This one is also important. So mean, okay, or expected value, variance, and standard deviation, important. Okay, so mark those as important. And know the difference, know how to calculate those for both continuous and discrete random variables. Continuous and discrete. So that's this lecture slide. Lecture 20. So lecture 20, we talked about some useful probability distributions. So we first talked about the Bernoulli random variables. Bernoulli random variables basically take on two possible values, true, false, head, tails, or success or failure. Okay, and typically we assign probability of 0 or probability of success with some particular value p, which is less than between 0 and 1, and probability of failure or 0 becomes 1 minus p. Okay. And the way we write the Bernoulli distribution is using this notation. We say X is Bernoulli distributed with parameter P, because if we know P, we know the probability distributions. Okay, so this one is easy. The probability mass function and the cumulative distribution functions are shown for this Bernoulli random variable. And the expected value of a Bernoulli random variable is P, always. The variance is also P. Sorry, the variance is not P. The variance is P times 1 minus P. Okay? And there are some examples. Okay? Now, after Bernoulli random variables, we have the binomial random variable. So for binomial random variable, actually you saw an example of binomial random variable yesterday, on Monday. Okay? On Monday I solved an example which involved both I think it involved both a uniform distribution and or some continuous distribution and binomial distribution. It was the first example that I solved yesterday. So it's essentially the probability distribution for the binomial distribution is like this. The probability that you take on a particular value y is n choose y. Probability of success is p. P to the power of y, 1 minus p to the power of n minus 1. Okay? The way we write it is using this notation. Y is distributed binomially with parameter n and p. And one observation we make is that if the number of trials n is 1, then we have the Bernoulli distribution. So binomial distribution is a more general form of Bernoulli distribution. Okay. So these are some examples of binomial distribution. Then we will introduce the Poisson distribution. So for Poisson, don't worry about it too much, okay? For Poisson, don't worry about it too much because we didn't also get to practice it that much. But again, it's an important distribution and it's used over and over in physics, okay? And the way it's written is like this. The probability mass function for it is given like this: e to the power of minus lambda, lambda to the power of I divided by I factorial. Okay? But don't worry about this too much.
Yeah.
The important property it had was that the mean and the variance were the same. Okay? All the mean variance were the same. They were lambda, the parameter for those values. Okay, so that's the Poisson distribution. Then we went on to continuous random variables. Okay, so continuous random variables, guys, is very important because I didn't get to test you on this in the assignment or a quiz or anything else. So that's why it becomes important. Okay, so because now I have a chance to test you on, this is the only chance I have to test you on continuous random variables. Okay, so therefore, I would definitely review this slide and the next slide. Okay, and also try to do some of those practice questions that I posted. Okay, so that you have time. I mean, obviously you're not going to do them tonight because by the time you leave you're going to be tired. But try it tomorrow morning. Okay, try some of those practice questions tomorrow morning so you can ask me during the lecture tomorrow if you have questions. Okay, so give yourself enough time. I'm not going to be here, guys, on Thursday. And on Friday at 12 noon we have our final. So So you basically have tomorrow to ask me for help. And, so make sure you go through this continuous random variables. Almost half of the questions on probability are from continuous random variables. Okay? So that's about 20% of the final. Okay?
From these two slides.
From these two slides and the practice questions that I posted.
Which two slides?
Okay? Sorry?
Which two slides?
Slide 20 something, 21st and the 22nd.
Huh?
No, 2 and 3.
Slides, I mean lectures. Lectures 21st and 22nd. Sorry, I'm getting tired too. So, lecture 21st and 22nd. Yeah. So basically for continuous random variables, this is what we said. Okay? We said when we go to continuous random variables, probability that your continuous random variable takes on a specific value is always 0. Okay? So when you go to continuous random variables, probability of x equal to 1 is always 0. X equal to 2 is always 0. X equal to pi is always 0. It cannot take any specific value. Continuous random variables, they cannot take a specific value. Probability means the probability has a meaning in terms of intervals, not specific values. Okay, so the only non-zero probabilities are going to have is when we're talking about intervals. Okay, so that means probability of, for example, x less than some value, x greater than some value, or x being within some value. So these are the 3 types of questions you could see. X less than some value a, let's say. Probability that your x is greater than some value a, and probability of x being between a and b. So these are the 3 possible probabilities that have a meaning. Probability of x equal to a is always 0. Okay, for continuous random variables. For any. Okay. So the questions you'll see on continuous random variables, if it involves probability, usually you'll see a range. Probability that it's greater than, it's less than, it's within. Okay? Now, we defined something called the probability density function. So again, this you should know. Probability density function, you should be able to describe what it is. And you should know its difference with respect to probability mass function. Okay, so you should be able, if I ask you what's the difference between probability density function and the probability mass function, you should be able to tell me. Okay? And the probability mass function, sorry?
What is it?
So basically probability mass function is defined for a discrete random variable, and it specifies the probability of that random variable for every possible point. Probability density function does not specify probabilities of any specific points for continuous random variables, but the area under it specifies the probability of any interval. The area within any interval specifies the probability for that interval.
Can you post that online? The exact
I just said it. he's recording it.
Yeah, I got it, don't worry.
Yes.
Yeah, he's recording
Does
it.
everybody know?
You don't know him, he's famous. So, the other property that's important, guys, this one, okay? When you integrate your probability density function from negative infinity to infinity, it should be equal to 1, okay? Again, important, okay? So basically, this is the case. For continuous random variables, if you have any interval, you're trying to calculate the probability that it's between 40 and 60. You look at the area of the probability density function, the area under the curve from 40 to 60, and that gives you the probability. Okay? And in case you wanted to know the difference between probability mass function and probability density function, there's also a slide for that. Okay? So if you really have read the slides, you would already know where to look. Okay? So, also, like I said, probabilities involving continuous random variables are like this. You have only 3 cases, and these are the 3 cases that I showed you. You're either dealing with probability less than, greater than, or within the interval. Okay? Now, cumulative distribution function is the same thing that we had for the discrete random variable. So the cumulative distribution function is actually the same for both the continuous random variable and discrete random variables. Okay? And the way they're related, the cumulative distribution function is related to the probability density function is using this formula. Okay? Another thing we note is that probability of x less than or equal to x, okay, in continuous random variables is equal to probability of x less than x plus probability of x equal to x. Because this particular probability is 0 for continuous random variables, you can see the probability that x is less than or equal to x is equal to probability of x less than x. Okay, so you can basically drop the equal sign. That's in continuous random variables, probability of less than or equal is equal to the probability of less than. That's essentially what it's saying. Less than or equal is equivalent to just less than. Okay? Now, again, like I said, probability of any specific value is 0. Any interval we're trying to calculate, it's the integral of the probability density function. Okay? Now, this example is important. Okay? So suppose x is a continuous random variable whose probability density function is given by this. So I give you a probability density function. Okay? And there is this constant c. Okay? And the question asks you, what is the value of c? Okay? So how would you solve this? So I've given you a probability density function, and I've asked you, what is the value of c?
C.
Hmm?
What is C?
No, you have to solve it. You have to tell me. I mean, yeah.
That's already
It's C.
solved.
Once you calculate the integral, and then because you calculate the integral is the c is going to come out. I don't know, something like that.
So yeah, you have to calculate the integral, c comes up. But then what? You have to calculate c.
The C is 2.
C is what?
2.
C is 2. Let me see if you've been studying or not. No, it's 2 over here. So you haven't been studying.
It just came up with a number.
Yeah. So here's, guys, the way we solve it. Remember that thing that I said it's important? If you integrate from negative infinity to infinity, the probability density function should equal to 1. Right? So what happens when I integrate my probability density function from negative infinity to infinity? Because it's 0 everywhere else except from 0 to 2, we go from 0 to 2 and we integrate. Like you said, c comes out of the integral, okay? And you integrate this from 0 to 2. You sub in the 2 for x, and then you subtract 0. You sub in 0 and you subtract that. So this part you should be able to do, this definite integral. And then you solve for c. You solve for c and you get 3 over 8. Okay?
So that would be 1 minus whatever inside the bracket is.
This one?
For C.
C would be 3 over 8.
I'm just trying to figure out how you got it.
Oh,
Huh?
so let me do it.
That would be 2 times.
So like, say you solve for C on the one side, it's saying if you bring it over, it will be 1 minus whatever you get for C.
No, I know where the problem comes from. You guys, when you guys see the integration, you panic. For some reason, the integration, I mean, you...
No, it's like you sub in 2 for every x you see, right? So that would be 2 times 2x.
So let's do it. 2 to the power of 2 is 4. 4 times 2 is 8, right?
Yeah.
That would be C, and that would be 8. And then you sub in 2 here, that would be 8. 8 times 2 is 16, so minus
16 over 3.
16 over 3, right? Now, when I sub in 0, everything becomes 0.
Yeah,
so in that case, I don't have to worry about it, right? Now, let's do this subtraction, okay? So I have to multiply this with, that would be 24 minus 16 over 3, right? And this whole thing should equal to 1.
Yeah.
So remember that the other side of the equality is 1.
Oh, you divided,
Okay?
okay.
So do
I got it. No.
Got it?
No,
Do you want me to go?
no, it's true.
So that's that. Now, if I tell you, now that you've counted C, you have the whole probability density function, right? Because instead of C, we put 3 over 8, we have the density function. Now, if I ask you find the probability that x is greater than 0, okay, so you should be able to calculate that as well.
C times 8 over 3 is equal to 1. But if you move it over the equality sign, it's a division. So it's 1 over divided by 8 over 8. It's 8 over 3. 3 over 8. They need to keep going. No,
that's fine. It's so this minus that, it's 8 over 3. Okay, so that would be C times 8 over 3, which is equal to 1. Right? Now I have to divide this side by 3 over 8. So I get C is equal to 1 over 8 over 3. Right? So I do this and I do that, and I get 3 over 8. Okay. Yeah. So we sub in the 3 over 8 here. Okay, guys. We sub in the 3 over 8, and now we are trying to find the probability that x is greater than 1. Okay. And now for the probability that x is greater than 1, we have to integrate from 1 to infinity. Right? The probability density function. Okay, because we want greater than 1. We go from 1 to infinity. But the thing is, this is 0 outside this interval 0 to 2. So we the integral range changes from 1 to 2, because for numbers greater than 2, the probability density function is 0. Okay? So we integrate from 1 to 2 the density function. And the value of density, I mean the formula for density function is this. And when we sub it in and we integrate, we get half. So the probability that is greater than 1, it's half. Okay? So important example.
I have a question.
Yeah.
For the, you don't use anything to do with 3 over 8, right? You just
From minus infinity to infinity of x multiplied with expected multiplied by the probability density function. Okay? And because it's important, the example for it is also important. Okay? So if I give you a probability density function like this, so this is a probability density function, and I tell you what is the expected value of x. Okay, you should be able to calculate it, because the expected value of x is equal to integral from minus infinity to infinity of x, f the probability density multiplied by the probability density function. And in this particular case, going from negative infinity to infinity, your probability density function is non-zero from 0 to 1. So the range immediately changes from 0 to 1. And now x times 2x is basically 2x squared, because the formula says x times the probability density function. Okay? X times the probability density function. And therefore x times 2x is 2x squared. And when you take the integral from 1 to 0, the answer is 2 over 3. So the expected value in this case is 2 over 3.
Are we going to get the formulas for probability density and probability mass?
You have a cheat sheet.
No, that's the thing. Like, if that's why I'm asking, do I have to put it on or not?
He posted it
Yeah, I've
already.
already posted like whatever I'm
So
gonna.
whatever you're giving is here, right?
Yeah, whatever it is, it's gonna be a 5-page basically.
Yeah.
Formulation. So that's the expected value. Also, the variance is important, guys. Okay, the variance is also important. So, like I said, variance is the expected value of x squared, and expected value of x squared is, instead of x times the probability density function, it's x squared times the probability density function. Okay, and this is just the mean squared. Now, when so this again, this is a good example, important example. So I had the same function. Now I want to calculate the variance. Okay, I had the same function. Now I want to calculate the variance. This one I calculated in the previous problem, like expected value of x. I calculated it. It was 2 over 3. Now I have to calculate the expected value of x squared as well, and that's equal to x squared times 2x. So that would be 2x to the power of 3. 2x to the power of 3. Right? So, let me write that as well. So we are trying to calculate the expected value of x squared, right? This is equal to integral from minus infinity to infinity of x squared, your probability density function, right? Now, my probability density function is 2x, right? And first of all, it's zero. It's non-zero from 0 to 1. So from 0 to 1, it's non-zero. Then I have my x squared, and for my probability density function, I substitute 2x dx. Then you see when 2x. Okay. So when I do that, I get that, and then when I do the calculation, I get 1 over it. So these are the three continuous random variable distribution: the uniform distribution, exponential distribution, and the normal or Gaussian distribution. So these are also important. And basically, uniform distribution has a uniform distribution. Its probability density function is given by this formula. So it's basically non-zero from some interval A to B. It's non-zero over that interval, and it's zero everywhere else. And within that interval from A to B, the formula for it is given by 1 divided by A minus B. So it's uniformly distributed. So yesterday I solved an example from involving the uniform distribution. It was the guy with the bus stop and the amount of time the guy had to wait. Okay, so that involved uniform distribution. And also the concepts from the continuous random variables applied there. So you saw we solve probabilities by integrating, right? By integrating over ranges. And so these are the plots for the probability density function. You can see it's zero everywhere outside A to B, and from A to B it jumps to the height 1 B minus A, and after B it just drops to 0. So yeah, there are some examples. Go through this. I solved an example yesterday. So all these continuous random variables are important. Exponential is not as important. It's like Poisson, okay? But uniform and Gaussian, they're important, okay? Uniform and the last lecture is basically on normal or Gaussian distribution. Okay, the last lecture is on normal and Gaussian distribution, and the formula for Gaussian distribution is this, which was complex. Okay, but there are only two constants here, mu and sigma. Okay, mu and sigma, and mu is basically the mean. Mu turns out to be the mean, and the sigma turns out to be the standard deviation. Okay, and mu specifies. It looks like this. It's a bell-shaped curve. Mu specifies its mean value, okay, or the center, and the sigma or the standard deviation specifies the spread. The higher the sigma, the more spread the bell-shaped curve is. Okay, and the way we write it is like this. We say x is normally distributed with parameter mu and sigma. Okay, sometimes they use n. Okay, because it's very popular. Normal distribution is very popular, and so that's the way the probability density function looks. Yeah.
Are we gonna have to use that formula, or will it be mostly just a lookup table?
It would be lookup table. It would be all lookup table. So yesterday I solved an example using the lookup table. You should be comfortable using the lookup table. Okay, there's a reason I included the lookup table in the formula sheet. That means you're gonna see an example where you have to use that lookup table. Otherwise, I wouldn't have wasted paper. Okay. So, like I said, the expected value or mean is mu. Variance is sigma squared. Standard deviation is sigma. And so this is an important rule. The data within one standard deviation of any normal distribution is 60% of the data. Data within two standard deviation of the normal distribution is 95% of the data, and 99.7% of the data is always between three standard deviation of the normal. Okay, So these are some examples. Go through these examples, and yeah, like I said, you should be able to solve questions using this. You have to be able to convert the formula that I gave you. The table that I've given you is the standard normal distribution table, and you should be able to convert any normally distributed random variable into the standard normal form, which is this z. Okay, and the way you do it is using this formula: x minus mean divided by standard deviation. Okay, and there are some examples of it. So please, like I said, these last two slides are important, and they're about 20% of your final. Okay, so go through them, and these are the examples of how to use the table. So if you don't still know how to use this table, I provide all the examples you need in these slides. Okay, all the examples are there. So go through those yourself, and because it's 15 to 9, I'm going to solve some of the questions that you wanted me to solve. So I'm going to stop, and I'm going to solve some of the questions. And also, guys, use tomorrow's tutorial or just lecture wisely. I mean, attendance for tomorrow's lecture, as I said, is totally optional. I'm going to be there. But if you guys want to stay home and study, do it. But please try to do some sample problems so that you could ask questions if you need to.